Hello everyone. In this video, we're going to be proving that R is uncountable, not using the diagonalization method. Okay, so no diagonalization, big word, but none of that. It's the typical way to show that R is uncountable, right? Instead, we are going to go more into the properties of R because I don't like the diagonalization method. And the reason I don't like it is because it says that every real number is some decimal expansion. And it's like, okay, but that isn't how we usually develop R, right? We don't usually call R the set of all decimal expansions because there's problems with that, right? You know, infinite non-repeating decimal expansions, blah, blah, blah. There's problems with that because that's not usually how we define R. I mean, it's not incorrect, but you know, a little strange. So what is R, right? R is it is basically the one and only complete ordered field. Now, I feel so stupid, but I always I always spell field wrong, so I don't want to make a mistake again. So forgive me. Complete ordered field, you know, with Q as a subfield. See, again, I have to check. And so what do all those words mean? Well, we will say that, complete tells us this is like the axiom of completeness, which means that all, like for all A subset R, A, is bounded above implies the supremum of A is a real number. Okay, so that's our axiom of completeness. So this is like the construction. Okay, so from these facts, I want to prove that R is uncountable. Well, not quite from this. So from the axiom of completeness, we can prove the nested interval property. Okay, and the nested interval property. So what this is telling us is that if I have a bunch of closed nested intervals, okay, so how should I write this? Maybe let me look at it for a second. And I have a video on the nested interval property, by the way. But so the nested interval property says that if we have a sequence of closed intervals, right? A sequence of closed intervals. And we also, let's call that, our IN. Looks like this. And we also have that IN, right? IN plus 1 is a subset of IN. Right? That's the bigger set for all n in n. So I have a sequence of intervals that are nested, right? So that means that each IN is a superset for the next one, or the next one's always in the previous one. Then this implies to us that the infinite intersection of all these sets is non-empty. And that's the nested interval. Nested interval property of R, I should say, I guess. Okay, so with that, we can prove. Okay, so that's going to be our star right there. Our star in the sense of the superstar of this proof, but also I will label it as the star fact. And that comes from the axiom of completeness. So if you want to prove on that, then I have a video on that. Okay, so how do we get that R is uncountable from this? Well, I mean, it's a similar proof by contradiction, okay? But we use this construction. Okay, so suppose R is countable. Right? That means that R is some sequence, x1, x2, x3, ... forever. But the point is it's countable, so that list contains all of them. Right? So we're going to contradict this. And we're going to do that by constructing a sequence of closed nested intervals which has to be empty, which would contradict the fact that it can't be empty. And when I say empty, I mean the infinite intersection. So this is how we're going to kind of do it, right? Here is our number line. Here's R. Here's 0, whatever. So then, x1, well, maybe I'll use a different color. X1 is maybe here. X2 is maybe here. X3 is maybe here, and so on, right? We jump around. And what we're going to do, okay, is this. For all n in n, construct in, right? Maybe you construct in plus 1, maybe, from in by, okay, well, we got to fill that in, right? We kind of be doing some induction here, maybe, so maybe I'll even start with the base case, right? So for I1, we're just going to take some closed interval that does not contain x1. So if we look at our picture here, I'm going to take some closed interval that does not contain x1. Well, we can just kind of do that, right? A1, B1. Then, for all n and n, construct in plus 1. So, maybe here we're saying n starts at 0. N starts at 1, maybe, for this. Motorcycle outside as I say that. But anyways, so yeah, we are constructing, maybe we use n starts at 1, whatever. Not a big detail. From in by, okay, and this is what we're going to do. So we're going to take the previous interval. So take in, split it into two, closed subintervals. Let's say one of which does not contain xn plus 1. Okay, what does that mean? That means I take this interval right here. That interval right there is our I1. To construct I2, I split this in two. I split this interval in two. Two closed, well, it doesn't matter, two, but just like I take it, I take a closed subinterval within it that does not contain I2. Now you see I2 is in this subinterval, right? But what I can do is I can just take maybe this, right? And that right there is my I2. It is a subinterval of I1 that does not contain I2. And I can always do this, right? So we can maybe go through a couple of cases based on some edges and things like this, but hopefully intuitively it makes sense that I can always do this. And then I would just continue, right? So my next subinterval would be a subinterval of I2, which does not contain a closed subinterval of I2, which does not contain x3. Well, x3 is not even in that interval, right? So I can basically just take any subinterval like that. And remember, between any two real numbers, right? Between any two real numbers, I have infinite real numbers in between them, right? So I can always find one. So I can always do this, right? I can kind of continue doing this over and over again. And the point is I do this for all of them, right? So now we see, right, that, consider the infinite intersection n goes from 1 to infinity of these in's, right? I mean, it must equal the empty set since, for all, let's say x in, x1, x2, x3, which is what we said R would be, x is not an element, let's say xi, right? Xi is not an element of what? Well, x1 is not in I1, x2 is not in I2, x3 is not in I3, so it's not an element of, interval I, which means that xi is not an element of the infinite intersection. And so we get this fact right here, right? We get that the infinite intersection of these closed intervals is empty. Closed, nested intervals is empty. But this contradicts the nested interval property of R. And so there we go. That's a bad square. There we go. We have it. That R must be uncountable. That this must not have made sense. So it really hinges on this construction of how we create these nested intervals. So I'm going to really focus on that one more time here, right? So we have the idea that we keep creating these these intervals, and each interval does not contain an element of it. If, so if we're on I2 here, right? I look inside I1, and I find a closed interval that does not contain x2. It's always possible, right? So what are the options here, right? X2 could be somewhere in between A1 and B1, in which case there's always going to be some, and not equal to the endpoints. Then there's going to be some, infinite amount of real numbers between here, so I could just choose any two of them. I want to probably keep them distinct, right? Probably makes sense to keep them distinct. And then we then want for the next interval, right? What if the element's on the bound? Well, if element's on the bound, I mean, again, the endpoints are distinct. So we can always choose another closed interval there within it. So this will always work. And so there we go. We have it that R is uncountable. All right. Thanks so much.